Hello everyone. In this video, we will learn about stochastic processes and how to study them through probability trees. Let me start with the definition of stochastic process. It's just a terminology, maybe fancy way of saying a sequence of stochastic or probabilistic experiments is called stochastic process. When you're studying stochastic process, you either should set up an order yourself, or it will be given in the sequence or in the stochastic process itself that okay, you will have an order. So the first experiment, then there will be second experiment, then there will be third experiment. So there is a standard or there is a natural order for these guys. Okay, so the examples that we study for our cases are something like, okay, let me put this one back in the place. Something like, okay, toss a coin twice. Okay, so you have experiment tossing a coin, you're repeating it twice, and well, in this case, you see that the result, outcome of the first experiment don't change the outcome of the second one. But in general, they can affect each other. So that's why this stochastic processes, specifically probability trees, are important. The other one is you take out a card from the standard deck. If it is hard, put it back and take it out another one. So that's a process, stochastic process with two steps, and you see that the result of the first would change the outcome of the second one. Okay, and the second thing here is another example is that let's say we have three containers with each one some number of white and black balls. So we first choose one of these containers randomly. So the first experiment is choosing a container. Then we, from the chosen box, we take out a ball. So then we study the probability of getting black or white ball out of that. Okay. Well, studying stochastic processes always is good to be done by something called probability trees. So probability trees are the tool to analyze a stochastic process. That's the best tool we have. But what is a probability tree? Okay, so that is the definition. Well, we have seen counting trees. So probability tree has a similar sorry about that. So probability tree has some similar properties, like a probability tree is labeled, directed, rooted tree with the following rule of labeling. Okay, so we have seen some of these things. Maybe you don't remember the terminology here, but directed means that grows from one direction from another to another, so growth usually we do from the left to right. Rooted means that everything starts from a node. We call it a root. So the first, basically, the most left one. And being tree means that, okay, so every node can be connected to the root through a unique path. Okay. So, well, before I go to the labeling facts, let us just draw something here. So we have A and B here, and then A and A complement. I could have B, but that means that's A complement. Then in the second experiment, you can get these ones. And well, there might be a third one, so I'll just do it something like C and C complement, and this can go on, yes? So far it's like the counting trees, but the point is that the numbers we put, the labels that we use for the probability tree are different, okay? So first of all, some sort of probability we will put on these edges. If it is on the first level, we just put the probability of the endpoint. On the other levels, you see, I want to find probability of the endpoint always, but since we are in the second level, we already see that A happened. So we have to put conditional probability of B knowing that A happened. And similarly, probability of B complement A, probability of B knowing A complement, and probability of B complement knowing A complement. How about in the third level? Again, so we always find probability of the event at the end node, but knowing all the events before that in the path to the origin, to the root, are occurred already. So this here will be B intersect A complement, and would be probability of C intersect C knowing B intersect A complement as well. Okay, so the rules of labeling here would be rules of labeling on the edges. In the first level, we have probability of endpoint or end node. For the other levels, we put a conditional probability. What would be that conditional probability? Probability of always the event at the end point or end node of the edge. So that is always there, like even in the first level. But in the other levels, you have to find conditional probability, knowing that Well, we know that already all the events along the path from the starting node of the edge to the root. So you start from the starting point, go to the root, and you see all the events along the way. You find intersection of those ones, because all those already we know happened. And that's the conditional probability that you will put on the events. Well, just very simple property. So I'll write this one as property maybe 1. There will be more to come. But this is very simple because from each point, whatever happened before happened. From that point on, the probabilities that coming out of one node should cover all the possibilities. So that means that they have to add up to 1. So probabilities on the edges coming out of a node must add up to 1. And this, you see, is clear. For example, if there are two edges coming out from a node, so probability of, say, any event here, B, knowing that something happened before, added to the probability of its complement, knowing that the same thing happened, is always equal to 1. So that's just a simple thing that you have to keep in mind. Remember, there was a similar rule in the counting trees, but the sum of the outgoings in that case must have been equal to the number on the coming in edge. Here, that's not the rule. Here, they must add up to 1 always. Okay? Okay. So having all this set up, let's just finish the video by one example. First thing here, okay, I have a probability tree with some missing numbers. Question says that complete the labelings and then find the given probability trees from there. Okay, so there's one rule here, the probability of the probabilities on the outgoing edges must add up to 1 for every node. So for example, for this node here, you see that there's half up there, so the rest will go to the other edge, which is half again. For this node, 2/5 is already out, so this must add up to 1. Here 1 minus 0 is 1, and here 1 minus 4/5 is 1/5, and that's the probability we have. Okay, the tree, the labeling is complete now. Now we are looking for probability of B knowing A. So what does that mean? It means that you found an edge whose end point is B, and the starting point starts from A, and then that would be the root. Okay, so here that is end point B, starting point A, and the path to the root has only one A. So that means that this guy here is what we are looking for. So 1 probability of B knowing A is 1/2. How about probability of B complement, A complement, the endpoint B complement, the starting point A complement? That will tell me that this guy is here. So the endpoint B complement, starting point, that is 2. probability of B complement knowing A complement, that is the number on that is 1. Yes. How about C knowing B complement and A? So this what's me endpoint. So there are two endpoints C, but this says which one we have to fix. B complement intersect A complement. It means that the path from the starting node of that edge to the root should contain exactly B complement and A complement. So in this case, so C is here, so you see that there is B complement here and A here. So that is the path. So the number we are looking for is this guy. So probability of C knowing B complement intersect A is equal to 2/5. And that was the 3. For 4, endpoint is C, but this time B complement and A complements are exactly the events along the path from the starting point to the root. So that is what we have, probability of C knowing B complement intersect A complement, which will give me this guy, 4/5. Okay, so in the other videos we will do some examples to set up a tree, and we will learn more about the properties or how to derive probabilities from a tree.